Yeah.
Oh.
Richard thinks it's a baby from after school. And Richard, tomorrow,
Okay.
I might probably could try to.
Okay. It's not long. Okay, hit record.
I already did.
Oh. All right, so if I asked you, we just took a test yesterday. If I asked you to graph this is a relation comparing X and Y. If you were to make a table, you could come up with some ordered pairs, right? That would satisfy this rule. If I asked you to graph this, you would begin at 1, right? And you would go, I'm making this as easy as possible, you go up 1 and over 1, right?
Yeah.
So all of these points that are on this line satisfies this rule, right? Okay, so now, let's say I came up with another equation, y equals negative x plus 1. I'm making this very easy. This one begins at 1 and it goes this way. So all of the points on this line satisfies this rule, okay? So there's infinite points that satisfies this rule, and there's infinite points that are on this line that satisfy this one. Hello,
I have 84s or 83s personally.
83.
83, okay. All right, thank you.
You're welcome. So now, if I put these two together, and I want to know what points do these two rules have in common, what the solution is where they intersect, okay? And in this case, it would be 0, 1. This is the only point that satisfies this and this rule, okay? So we call this a system of equations when we put 2 on 1, and we're asking you to find out what point, or there could be points, or there may be none, that these two have in common. So that's what you're going to do today. We are going to investigate systems of equations, which is a collection of equations using the same two variables, and we're going to look for the ordered pair that satisfies both equations, okay? Now, we're looking at where those two lines intersect. So there's 3 situations that could occur when we take 2 lines and put them together. They could intersect in 1 point. And if that's the case, there's exactly one solution. You're going to name it. Sometimes they could be the same line. And if that's the case, there's infinitely many solutions that satisfies the system. And the ordered pairs are all the ones that are on that specific line. And if they're parallel, do these 2 points ever collide? No. This would be no solution. So we might have one solution, infinitely many solutions, or no solutions. Okay? Now let's talk about the 2 lines. Let's classify them. If the 2 lines intersect, or they don't intersect, they are independent lines. So this one these are independent, and this is also independent. Could you write independent right here for me? Independent. Okay, so if the 2 lines are doing their own thing, they're independent. But if it's the same line, they're dependent. When one moves up, so does the other. They're dependent. If you get an answer, it's a consistent system. These are the classifications. So we got an answer here. We got one answer, one solution. And this one is also consistent. We got infinitely many solutions. So consistent means, can you get an answer? Is there any area that there's common to both? And so these 2 are consistent, but this is inconsistent. An inconsistent system doesn't give you an answer. We have no answer. Inconsistent is there's no solution. Okay? So we can describe the lines. Are they independent? These 2 are independent lines. and this one's dependent, and we can describe the solution. It's consistent, these two are consistent, and this one's inconsistent. All right, now let's talk about the slopes in the y-intercepts of these cases, these three cases. In this case, can you describe their slopes? Are they the same or different? They're gonna be different. One's positive and one's negative in this case. So the slopes are gonna be different if it's one solution. And their y-intercepts will be different also, okay? On this one, well, if they are the same line, what do you think their slope and their y-intercepts are gonna be? The same. It's the same line. So look for that. Look for the same slope, same y-intercept, and then it's infinite solutions. Now for this one, what's going on with the slope? It's the same slope. But what's their y-intercept?
Different.
They're starting in different spots. Okay? Now, let's take a look at this for a second. If there's infinite solutions, how do we write the answer? So for this one, can you give me the equation of this line? Let's pretend like it starts at 4 and the slope is -1. What's the equation of this line? It's y equals -1x plus 4. So in this particular case, there's infinite solutions on this. So how we will write this answer, instead of writing infinite solutions, because infinite solutions sounds like anything you pick will be a solution. But we want to be specific to what lies on this line. So this is how you're going to write this answer. You're going to write bracket all the points x and y such that, and then you write the equation. So all the points that lie just on this line. That's how you write the answer to infinite solutions. You write bracket and you write x, y such that y equals, you're going to write the equation of the one line. Okay? So you're saying all the points that lie on this line are a solution. Okay? So let's do 3 examples on the back. Number 1. How will you graph the line 2x plus y equals 3? You have 2x plus y equals 3. I need to see the picture of this relation. So what am I going to do? How do I graph this? Rewrite it in slope-intercept form. So simply subtract 2x, and you get that. Y equals -2x plus 3. How do you graph that? Begin at 3, and your slope is it's a 2 to 1 ratio. So you're going to go down 2 and over 1, and you can go up 2 and over 1. But just make sure your line's going negative. And we connect the dots. So all of the points satisfies this line right here. Next, go to the next equation. So you have 3x minus 2y equals 8. We have to graph this one. So bring the 3x to the other side. Make it -3x. And divide everything by -2. So you get y equals 3x, 3 halves x minus 4. So I know that their slopes are different. They're going to collide. They're going to intersect. So begin at -4. And you go up 3 and over 2. And I'm hitting the line that I want to hit. Up 3 and over 2. So what is a graph? It's a picture. It's a visual for us to see where these two relationships are going to collide. Now your job is to explain where is the location, where's the direct hit. Can you tell me what ordered pair that is?
2 -1.
What is it?
2 -1.
2 -1. That would be the solution. So the solution to this system is the ordered pair 2 -1, right there. You went over 2 and down 1. Can you describe these two lines? What are they doing? Are they parallel? They're intersecting. They're intersecting. They're intersecting lines. And are these lines independent or dependent? Independent, they're doing their own thing. They're independent. And if we get an answer, it's a consistent solution. So this is it's a consistent solution because we got an answer and the two lines are independent. So you will get like 6 points on your test for that. Now let's look at another case. You're not going to be happy with this one because it's a fraction, but we can still do it. So we end up with, we have x, let's do x minus 2y equals 3. How do you get this in slope-intercept form? Subtract x, then what?
Divide it by -2.
Okay, so everybody be careful with this one because you end up with 1/2 x. Convert this to a decimal. What's negative 3 over 2? Negative 1.5. So where is negative 1.5? It's right there. And we're going to go up 1 and over 2. Just 1 right in the middle and 2 right in the middle. Just like that. No big deal. Connect your dots. Now we look at the second equation. It says, I'm going to write it the other way, 2y equals x plus 5. All I did was write it backwards, write it the way I slope-intercept form, and divide everything by 2. So this one is y equals 1/2 x. What's another name for 5 halves in decimals? 2.5. So this one's beginning at 2.5, but look at what's the same. So where is 2.5? It's between 2 and 3, but it's got the same rate of change. The slope is the same. It's down 1 over 2. So how would you describe these two lines? When will they hit?
Never.
Never. These two lines are parallel. They will never, there is no solution. There is no solution. These two lines describe them. They are parallel. Are these lines independent or dependent? They're independent lines. They're independent lines. And we didn't get an answer, so our solution is inconsistent. Add that to your, this is an independent, they're independent lines. No answer is no, it's inconsistent. In the last example, let's get this in slope-intercept form. We have x minus 3y equals 6. That's this one right here. So I'm going to subtract x and then divide by negative 3. So y equals 1/3 x minus 2. How do we graph that? We begin at negative 2 and go up 1 and over 3. And the second equation, I'm going to subtract 12, so 2x minus 12 equals 6y. Divide by 6. So 1/3 x minus 2 equals y. Well, guess what? It's the same line. So if I graphed it, it'd be right on top of that one. So what would be the solution to this? It's infinite solutions, but see if you can remember how to write the answer. Anyone know?
Sideways 8.
Bracket, sideways 8. In the bracket, and then do x comma y, such that, and then just write y equals 1/3 x minus 2, and then end your bracket. Describe these two lines. They are what? They're the same. They're coinciding. They're the same line. Are these lines independent?
Dependent.
They're dependent. Did we get an answer?
Yes.
Mm-hmm. This solution is consistent. We got more answers than we want. We got many answers, and this is a consistent system. Now, in the real world, think of these three situations as, if I were to say, for this one, meet me at Hall Road in North Avenue. Okay, just Hall Road, meet North Avenue in one spot, it does. Okay, I know there's 4 corners, but think of it a straight line. Hall Road and North Avenue, they cross, right? This next one would be like, this parallel one, this would be like, meet me at Hall Road and 21 Mile Road. Can you meet me at Hall Road and 21 Mile Road?
No.
No, they never hit. And then this one would be like, meet me at Hall Road and M59. Hall Road and M59 are the same thing. Does that make sense? So that's like a real world of these, okay? So that's how I remember. Okay, flip this over. Number 4. Without graphing these, using algebra, could you rewrite them in slope-intercept form and analyze their slopes and y-intercepts and tell me, are these independent, dependent, consistent, inconsistent? So go for it. Number 4. How do you get y by itself here? We've got 4y minus 2x equals 6. Yep, add 2x. And then what? Mm-hmm. And I'm just going to reduce my y-intercept 3/2.
Can't you just make this one equal?
Huh?
Oh,
Yeah, you
1.5.
could. You could write 1.5 if you want. How about the second one? Can I just put divide 8? You mind if I just shorten it? Can you reduce 12/8? What number goes into both of these? 4. So that'd be 3/2. So now look carefully at these two and tell me, what's the solution? There is none. Why?
Because they have the same.
They have the same slope and different y-intercepts. Now, if you would have made a math error and wrote +3/2, you would say that they were the same. So be careful. So these two equations, the lines are independent, but the solution is inconsistent. Why? Because they're parallel lines. There is going to be no solution on this. These are parallel lines. In number 5, try that one. 3y equals negative 2x plus 1, divide by 3, and y is negative 2/3 x plus 1/3. And the other one, when you slide 4x to the other side, you end up with negative 4x. So what would you say about these two? These two slopes are completely different. So as long as the slopes are different, the lines are independent, we are going to get a consistent solution. Mm-hmm. You're going to get one answer. They're going to intersect. There is one solution, and your job is not to find it, but just to classify these two lines. Okay? Now, the graphing method is not always a good method. Tomorrow we're going to investigate another method. But here's a story problem I want to introduce to you to start you thinking, because we tend to struggle on these story problems. So the more story problems we do, the better we will get at them. Here is one example. And I want you to start to develop patterns throughout. You're going to see a common thread in a lot of these story problems, and they're not that hard. So let's read this. A store sells two kinds of notebooks. We have the two different notebooks that we're talking about are small notebooks and large notebooks. We're selling, we purchased how many? 6 notebooks, 6 total. And the cost of each is $8 and $10, and we spend $56. We want to find out how many of each notebook did this person purchase? How many of the small ones at $8 and how many of the large ones at $10? Spending $56 and purchasing 6 of them. Okay, so now, what are the two quantities that we're dealing with? Small notebooks and large notebooks. You've got to decide what letters you want to use. Some people like to use the letters of what you're talking about, like S and L. You like that, S and L? Okay, so let's say S is our small notebooks, and L, use a capital L, because it looks too much like a 1, in large notebooks. Your first equation, we're purchasing these 2 items, and your first equation is going to be, how many items of these 2 are you purchasing? What's the total number of notebooks we're buying? 6. So I want you to think, we have small notebooks and we have large notebooks, and we're buying a combination of 6 items, 6 units, okay? Now, the next equation is how much each of these costs. How much is a small notebook? Attach that to S. So we have 8S, so the cost times the number of notebooks, and how much is a large notebook? 10 times S, and how much did we spend goes with this 56. Now,
Why did you put S next to the 10?
oh, I'm sorry, L. Thank you. L, good call. L, $10 for each large notebook. Now, if we wanted to graph these 2, we could, but you're going to see if you tried graphing it, and I was going to show you and let you see how the graphing method is not always a good method. And in this case, it's not good, because when you go to graph the second equation, you're going to see decimals, and it's going to be really hard to see where they intersect. So there's another method, and I know you guys know what method I'm talking about. Do you remember multiplication? Do you remember how to solve this another way? And we're going to do this tomorrow, but I thought this would be cool to start off with. Do you remember how to get, if you were to add these 2 up, how could you add them and eliminate? It's called elimination. Do you remember to multiply one equation by something? How about -8? If we multiply this top equation by -8, remember this? Okay, so let's go through and distribute -8 with the top equation. What do you get? What's our new equation? -8s
Or minus 8L
equals
equals
-48. Don't forget this number too. Now we copy the second, leave the second equation alone. Is this coming back to you? Okay, what do you do now? Add them up, and what's -8L plus 10L? 2L equals, what's this? Anyone? 8. And what's L? 4. What does L stand for? The number of large notebooks. How would we find out the number of small notebooks? You're going to plug 4 right in here and subtract it, and what's S? 2. So in other words, 2 small notebooks. So I'll finalize your answer by writing it in 4 large notebooks. Does this answer make sense? It should. Add them up, and you should get 6. And you could take 8, multiply it by 2, and then 10 times 4, and you should get $56. Easy? So, for homework, look to the back. Yes.
Where did you get the 8 from?
8, it's
The
8,
negative
8 now. Oh, where did I get the 8 to figure out?
8. Yeah.
Okay, see there's an understood 1 here? In order to add two equations together and eliminate them, you want one to be a positive and one to be a negative. So I see the 8 here, so if I multiply this by negative 8, they will eliminate. You get it now? I could have used a negative 10, and you'll get the same answer. All right, for homework, what are you guys gonna do? The back side, you have 6 questions for homework. I will put these on YouTube, okay? So make sure you have them all done tomorrow when you get here.
We don't have the last, we don't have the last one.
No, these are all graphing.
Do you have any voices?
What?